Okay, so we have a test on Friday. The test is going to cover from where we left off last time up through probably where we end off today. So definitely all the alkene reactions, E2, probably some SN1 and SN2, and E1s. So I would look at E1. I would look at SN1, SN2, E1, E2, particularly with alcohols. The E2 with the strong bases, and then the reactions of alkenes. So wherever we left off, just from that point forward. Okay, so, and Wednesday I'll answer questions about anything that you would like questions answered about. All right, okay. So I figure out where we're at here. All right, so where we left off last week was the reactions to add H and OH across the double bond. And so we were at the point saying, okay, if you add H plus and H2O, you end up Markovnikov, but you also end up with these adding 50-50 cis-trans, because this involves a carbocation intermediate. If you do mercuration, demercuration, you're going to end up adding the H and the OH Markovnikov, but 100% trans. And the reason it's 100% trans is because we make the mercurium triangular intermediate. And then the last one that we ended with was hydroboration oxidation, which adds H and OH anti-Markovnikov and 100% take a guess. Cis. Because it adds the H and the boron to the same side of the double bond. Okay, so that just gives us a variety of ways to add H and OH. At some point, we'll begin to think kind of in reverse. In other words, I might say, I might give you the reagent or the reactant and the product and say, well, what reagent would you use to go from there? And you'll have to look at that and say, oh, well, I'm adding H and OH anti-Markovnikov. So you'd use hydroboration oxidation. Okay. But right now, let's just be able to go in the forward direction instead of reverse. So the next topic then that's kind of related to this is the idea of epoxides, or the IUPAC name of an epoxide is an oxirane. And so an epoxide is a three-membered ring with an oxygen in it. So it's a three-membered ether. And these turn out to be pretty good intermediates. And by intermediates, I mean an intermediate compound that we can make because we can use them to make alcohols. And the way we're going to make alcohols is we're going to open up the three-membered ring. So the reason I put epoxides in here now is because if you go back and remember bromonium ions and mercury ions, we now have that triangular intermediate, which is going to be exactly what this is. Only these are actual compounds. You can isolate them, you can put them in a bottle. You hear about epoxy resins, sometimes like super glues and things like that. Well, that's these compounds. So, how do we make them? Two ways. First, the long way. The long way to make epoxides is to first of all add bromine and water. And when you add bromine and water, what do you add to the double bond? A bromine and an OH group. How do you add it? Markovnikov, anti-Markovnikov. Markovnikov. But again, we get back to what we said last week. There's no H. So what does Markovnikov mean? I'm going to add the Br plus as my electrophile, and my OH is my nucleophile, except it's not really the OH, it's the water. So I'm going to add a Br and an OH to the double bond. So the Br plus then is my electrophile, and so that's going to add to the carbon with the most hydrogens. That's my electrophile. So the broad definition of Markovnikov addition is when the electrophile adds to the carbon with the most hydrogens. But it doesn't have to be an H plus at this point. It can be any electrophile. Last week it was mercury. All right, and then the OH adds. So I add a Br and OH, Markovnikov. How do they add? This goes through a bromonium ion, which means the Br and the OH add. How?
Trans.
100% trans. How'd you know that?
Because it's on the board.
You could have looked much more impressive had you have said, because it goes through a triangular intermediate.
That too.
Don't worry, there'll be more times. But anything that goes through a triangular intermediate always adds 100% trans. So we make our bromohydrin then. So we add the Br and the OH. Now, if I take that bromohydrin and I react it with hydroxide, the hydroxide will come in as a base and it'll deprotonate the OH of the bromohydrin. And it'll make this alkoxide. And remember, terminology-wise, an alkoxide is just a deprotonated alcohol. But alkoxides are great bases, but they are also very good nucleophiles. Particularly in this case, because this O- can backside attack that carbon and kick off the bromine. It's in a perfect position because the Br and the OH added trans. So they're in a perfect position to do SN2. Okay, in this case it's an intramolecular. It's an intramolecular SN2 reaction, meaning within the same molecule. But now we can close the ring and we can make an epoxide. So, if you, before when we were looking at bromohydrins, it was like, oh, what are they useful for? Primarily just this. You can use them to make epoxides. And it's all because the bromine and the OH added 100% trans to begin with. Okay. Everybody with me? So then, there's another way, which is actually the easier way. And that's to take and use a peroxy acid. So a peroxy acid is an acid that has two oxygens in the OH. So hydrogen peroxide is HOOH. So peroxy just means there's one more oxygen present. So a peroxy acid will look like that. It's got a C double bond O, OOH. And what happens is that this oxygen in the peroxy acid ends up adding to the double bond. And so it adds to the top, it adds to the bottom, but what we end up doing is we end up forming the epoxide directly. Okay. So it's a one-step reaction. But it introduces a new term that you'd think would mean something else, but it doesn't. And that's stereospecific. Okay, remember that we had regioselective. Regioselective means that you have a reaction that makes two different products, or has the potential to make two different products. Those products are, for regioselective, the products are structural isomers, and the reaction selects one over the other. That's regioselective. What was stereoselective? You got a reaction that has the potential to form two different products. Those products are stereoisomers, and it's selected one over the other. Well, remember that we said selecting means anywhere from 5149 all the way up to 100 0. There was no term that differentiated 100 0 from anything less than that. You would think that this term does, but it doesn't. So stereospecific actually deals with the other end of the reaction. In selective reactions, I'm talking about a single reactant or pair of reactants making two different products. In specific reactions, we're talking about the different reactants making different products. And so this reaction is stereospecific. So what do I mean? Well, let's say that I had the cis alkene. If I have the cis alkene, I'm going to make the cis epoxide. Because in this mechanism, the oxygen of the of the peroxy acid, that oxygen just plops right on top of the double bond. And then it adds to both carbons at the same time. So there's no way that the oxygen would add to one carbon and you'd have the ability to rotate around the double bond and form the epoxide that way. So whatever the starting stereochemistry was, that's the stereochemistry of the product. But what stereospecific means, it means that if I changed the stereochemistry of the reactant and I reacted this with a peroxy acid, I would then get the trans epoxide. So in stereospecificity, what it means is that if you change the stereochemistry of the reactant, you will get a different product. So in this case, if I start with trans, I get trans. If I start with cis, I get cis. So by changing the stereochemistry of the reactant, I got a different product. Right? And that's what stereospecific means. We've seen another example of a stereospecific reaction, where if we change the stereochemistry of the reactant, we get a different product. Anybody want to take a guess as to what the other stereospecific reaction that we've seen is? I'll give you a hint. SN You got a 50-50 shot. SN2. Why?
Because when it adds, it flips from R to S.
So if I start with R, what do I get? S. If I change the R to S, what do I get as a product? R. So it's stereospecific as well. So the idea here is that stereospecific doesn't mean that you retain or you invert stereochemistry. It just means if you change the starting reactants stereochemistry, you get a different product. In this case, cis becomes cis, trans becomes trans. But in SN2, R became S and vice versa. But those were examples of stereospecific reactions. Okay. So this is stereospecific. And I can make the epoxide in one shot. Now, MCPBA, what does that mean? Sometimes you will see a very specific type of peroxy acid used. And here is that compound. That's called metachloropurbenzoic acid. And we'll talk about its structure next semester. Jericho.
So stereospecific is when you start with and change the reactant, the configuration of the reactant, and you get something different. But isn't that the opposite of starting with a cis and then getting a cis?
Yeah, and stereospecific doesn't mean that it's either retained or inverted. It just means that one gives one, and if I change the starting, if I change the reactant, I get the other. That's all it means. It means this reaction doesn't give me 50-50. So it's not. So I don't get a mixture of both of them. Some stereospecific reactions, you end up with the same stereochemistry. Other stereospecific reactions, you end up with the opposite. So it depends on the reaction. This one is the same. So that's what MCPBA is. You'll see its structure, but it's a very specific peroxy acid. So this is one step. If you want to make an epoxide in one step, this is what you do. So the reason we make epoxides is to open them up. And so we're going to, at this point, talk about acid-catalyzed ring opening. And sadly, that acid-catalyzed term may or may not really be a catalyst. So let's just say, for the sake of argument, I made an epoxide. Now I want to open it up. Because ultimately, epoxides are used to make alcohols. So I add acid to it. And what's the first step of the reaction? Well, the first step of the reaction is when you add acid to something containing oxygen, you protonate that oxygen. So we do that. And so when we protonate that oxygen, we end up with something that looks like this. Although really I could write this, and I would actually leave out the OH, or the delta plus on the OH, and I would say it kind of looks like that. The oxygen really doesn't want a positive charge. Carbon is better at taking the positive charge because it's less electronegative. So I see a triangular intermediate with a positive charge, and what do I think? I think bromonium ion. Whether you think that or not, hopefully you can say, oh yeah, okay, maybe I think about that. But we have a triangular intermediate with an overall positive charge. It's going to look like the bromonium ion, which means that my carbons are going to share delta positive charges. So I spread out the charge and made the molecule more stable. Well, now what can I do? Now I can add a nucleophile to it. What kind of nucleophile? Oh, let's say I added H2O. Or let's say I added Cl minus. The Cl minus coming from HCl to begin with, because I needed the H plus to protonate the epoxide. So we're stereochemistry-wise, where are those nucleophiles going to add to that protonated epoxide?
From underneath the triangle.
Opposite the OH. I'm having a sense of deja vu, which I have quite often, whether it's real or not. Where have we seen this before? Where did we see this last week? I know last week seems like a million years away. Trust me, it does for me too. But we have 2 weeks left. Let's just suck it up and get it over with. Actually, you have 3 weeks left. Right? Because you don't want to quit before finals week. That's bad. That never ends well if you quit before finals week. The end of finals week. Where have I seen this before? Bromonium ion. Mercury ion. The triangular intermediate. Right? So these are going to add 100% trans. And so that means that if I added the water, what's going to happen? And I'm going to bet that I don't. Oh, I do. So if I have my epoxide, my protonated epoxide, my water is going to do what? It's going to come in and add to that carbon. But if it comes in and adds to that carbon, what has to happen? This carbon-oxygen bond better break. And so that pair of electrons will go to the oxygen, which is perfectly fine because the oxygen only had a lone pair to begin with. So when I do that, what happens? My OH ends up here. My oxonium ion ends up down here. And what's the final step?
Hydrogen bonds forms
Like that. I'm going to lose H plus. So I now will have added my OHs overall. I added 2 OHs trans to the double bond. And in this case, when I use H plus H2O for this reaction with the epoxide, I'm not concerned where the OH added, because I added 2 OHs.
Why is it on the last slide that there was this?
Because it was a typo.
Okay.
Because on the last slide it was a typo. So it should have been an OH there and an OH there. So if I add H plus H2O, I'm going to end up with 2 OHs added 100% trans. So in other words, let's take all these reactions and kind of string them together. So if I said I have a double bond and I want to convert that to adding two OHs across the double bond. I want to go from alkene to what on the previous slide was a vicinal dialcohol. I can't do it in one step. I've got to do it in multiple steps. So what I'd end up doing is converting the alkene to an epoxide and then adding H plus H2O to the epoxide, and the net result is that I've added H and OH 100% trans. And there is no real there's no Markovnikov or anti-Markovnikov to this. Number one, because it's two steps, but also because I'm adding two OHs. But I can't do this in one step. I can't add two OHs trans in one step. I've got to do it in two steps.
Where does the oxygen come from?
Where does the oxygen come from? It comes from this.
Oh,
Or bromine, water, and NaOH. Right, if I want to go through the bromohydrin like I started with. So there's two ways to make the epoxide. I can make it with the peroxy acid, or I can make it with the bromohydrin. It's just easier one step with the peroxy acid. Right, so now what I'm starting to show you is the idea that we can do these transformations and we can think about putting steps together. So if there was a one-way method, if there was one-step method to go from double bond to trans dialcohol, I'd show you that, but we don't have it. The only way we have to go from alkene to trans dialcohol is two steps through the epoxide. But that epoxide would let me do lots of things. I could add HCl. And if I added HCl to my epoxide, let's see, I probably don't have another clean slide, do I? Of course not. So if I took my protonated epoxide, and now let me add two hydrogens and two R groups. And now I said, well, let's add HCl to the epoxide. So the H plus added to the epoxide now produces the protonated epoxide. Now if I added Cl minus, where's the Cl minus going to add? Is it going to add to the left carbon? Is it going to add to the right carbon? Or is it going to add 50-50?
Would it be the left because it would end up being more positive?
So I put my delta positive charge on the carbon. Which carbon has the greatest delta positive charge? The one on the left. Why? Because it's the most give me a word. It starts with S, not that word. The most substituted. Right? Again, I'm having this strange sense of deja vu that apparently nobody else is having. Well, you better by Friday. So the Cl minus is going to add here. And so now what I'll end up with is adding the Cl to this carbon. The OH will end up over here. So now I will have added my Cl to the most substituted carbon. My OH will end up on the other carbon. And that's what we did when we did Br2 in water. And we started talking about this last week with the mercury ion. Jericho.
What makes the left carbon the most substituted in comparison to
The two R groups.
the two R?
So if we were thinking about, and I did this back last week, if we're thinking about which carbon has the most delta positive charge, this carbon would look like a tertiary carbocation. That carbon would look like a primary carbocation. The tertiary carbocation would be more stable. And therefore that would have the most positive charge. And remember, if you're a nucleophile, you have to react with the carbon with the most delta positive charge. You've got to give to the most needy. And the most needy carbon is the one on the left.
Why in the last two examples did you add the water to the right carbon? Is that just
It didn't matter. Actually, that didn't matter in that case. So I could have added it to the right or the left. The simple fact of the matter is I'm going to end up with two OHs.
right?
Honestly, I don't know where the water added. Because they're two OHs, I can't tell the difference between them. But now if I make this unsymmetrical, I am going to be able to tell that the chlorine added left and the OH ended up on the right versus the other product.
If there was carbons that were attached where the R's are, then would it be the left then that would have gone towards? Yeah.
The OH would have added to the left one. But we wouldn't have been able to know that. Because in the end, we would end up with two OHs. We didn't know which one came from the epoxide or which one came from the water.
I was talking about the reaction on the far right.
Same thing.
Okay.
In the end, we'd end up with two OHs. I don't know which one came from which, unless I do something. So if I make it asymmetric, that definitely tells me which one it's adding to. Okay. All right, everybody kind of with me? Okay, so that all of those were examples of electrophilic addition. Add electrophile, add nucleophile. Now we've got a whole series of double bond reactions that aren't electrophilic, meaning that the mechanisms don't involve an electrophile and a nucleophile. Instead, just going to add two things to a double bond. So going through these, hydrogenation. Hydrogenation is a reduction reaction. Again, going back to what I think I said a few weeks ago in lab, when we did our reduction of the yeast reaction, oxidation and reduction in organic chemistry ultimately end up with whether you gain or lose electrons, but it's hard to determine that. So in organic, we talk about oxidation as when you gain oxygens or you lose hydrogens. Reduction, gain hydrogen, lose oxygens, opposites. So this is reduction because I'm going to gain two hydrogens. And that's what the first paragraph says. So I'm going to add hydrogen gas across the double bond, add two hydrogen atoms. I need a catalyst for that. My catalyst is either a palladium or a platinum metal. Okay, and so we just basically take our alkene, we plop it in the solvent, we bubble in hydrogen with the platinum or the palladium, and we reduce the double bond to a single bond. Okay, as simple as that. It's done every day. Maybe I'll give you an example of where you would see that. Can't be regioselective because I'm adding two hydrogens. Adding them this way or this way, same product. No regioselectivity. However, it could be stereoselective, because it turns out the hydrogens add 100% cis. Why? Well, the mechanism for this reaction is probably, in its ultimate nitty-gritty details, I don't know that it's fully known, because this involves the surface chemistry on a palladium or platinum. But here's how we can imagine it. Hydrogen gas sticks to the surface of the metal. Then the pi electrons here end up coming close to the metal, and the hydrogen will add to this carbon, the other hydrogen will add to that carbon, and it happens all when the alkene approaches the metal. So there's no approaching, adding one hydrogen, flipping around, and then coming back. It has to add one step. So the hydrogens add to both carbons in one step. And that means that they add 100% cis. Okay. So that's how we hydrogenate a double bond. It's as simple as that. Let me go back. Where have you seen hydrogenation? Where do you see the products of hydrogenation? There are these things called triglycerides. Triglycerides are the triesters of glycerol. Glycerol being CH2OH, CHOH, CH2OH. Put 3 long-chained fatty acids on them, and you make a triglyceride. What's a triglyceride normally known as outside of science class? A fat, or fat's a solid. What's the liquid version of a fat?
Oil.
An oil. And that's technically how we define the difference between fat and oil. Fat's a solid, oil's a liquid. But they all are triglycerides of long-chain fatty acids. Well, some fatty acids have nothing but single bonds. They are called unsaturated fatty acids. Some fatty acids have a double bond stuck in them, or more than one double bond stuck in them. They are called unsaturated fatty acids. And I forget which is bad, and which one is not as bad. But nutritionally, one is worse than the other. And it turns out that the straight single bonds are fats. And when you put a double bond in there, you turn it into an oil. It's the way it works. So what they do is they get plant oils, like coconut oil or other oils, and they want to make them fats. They want to make them solids. So what do? They take their unsaturated fatty acids and they add hydrogen to them. They hydrogenate them. And so the liquid oil turns into solid fat. Welcome to Crisco. That's what it is. It's solidified oil by hydrogenation. Of course, what happens when you only partially hydrogenate the oil? Then you get partially hydrogenated fats, which I think are the most evil of all, for some reason. So you see the products of this all the time. Okay? That's the hydrogenation process. And so it's relatively straightforward. Hydrogen, palladium, double bond, you make a single bond. It's as simple as that. But that will never be regioselective And if adding the hydrogen cis or adding the hydrogens trans produce different products, you selected cis over trans, then it would be stereoselective. Oh, what else can I do? Well, this one I don't do very often. We can do what's called carbene additions. So carbenes are incredibly reactive species. They are carbons with no charge, and they own 4 electrons. They only share 6. So it's a carbon with a lone pair with no charge. Well, these carbenes basically do the same thing as the oxygen in the peroxy acid. What happens is think about taking this pair of electrons, forming a carbon bond that way, taking that pair of electrons and forming the carbon-carbon bond that way. We will have added our CH2 directly to the double bond, and we make a cyclopropane out of it. Cyclopropane rings are incredibly difficult. Carbenes, let us make them relatively straightforwardly. So you end up producing a cyclopropane. This reaction doesn't fit the regioselective term. Regioselectivity can only occur when I add one thing to one carbon, another thing to another carbon. However, let's just say for the sake of argument that I use the cis, and with the cis I get the cis cyclopropane. So cis-alkene makes cis-cyclopropane, trans-alkene makes trans-cyclopropane. How would I describe this reaction?
Stereospecific.
That would be stereospecific. So carbene additions can be stereospecific. There's different ways to make carbenes. Some of these involve some reagents that are quite exotic, some reactions that you have to be careful that you don't blow yourself up with. Diazomethane is one of those. Diazomethane is CH2N2. There are 2 resonance structures of diazomethane. Whenever you make a molecule where you have a gas molecule embedded within it, like diazomethane has a nitrogen gas molecule within it, you got to be careful with those because if they form a gas, they usually give off energy. You have an incredible expansion of volume, and when you heat a gas, it expands even more. So sometimes you end up with, you can take a solid, and if you make a gas out of it instantaneously, that's bad, because that means explosion. So if you want to make a good explosive, embed a gas molecule in your molecule. That's how all the good explosives are made. Don't do that, but that's how they make them. So diazomethane we have to be careful with, but what happens is when we either heat cautiously or shine ultraviolet light, we end up cleaving off the gas molecule and we make the carbene. And then the carbene immediately adds to the double bond and we make our product. So that's the classical way. There's a little bit more stabilized method called Simmons-Smith. In the Simmons-Smith reaction, we take diiodomethane. So this is like the iodine equivalent of dichloromethane. And if you react it with zinc and copper mixed together, you will end up forming the carbene, only it's a little more stabilized because it's attached to the zinc. So you avoid the explosion possibility. And then you can do alpha elimination by taking hydroxide and reacting it with a trihaloalkane, like in this case, tribromomethane. And what happens is that the OH is able to deprotonate the hydrogen, and you're able to make this anion. That anion loses a Br minus and ends up forming a dibrominated carbene. And that is then going to react. That reaction is fairly easy to do. There's a solvent that we use that you'll use next semester in lab called chloroform. That's this. CHCl3 has a common name of chloroform. And one of the things we have to be careful of with chloroform is that we never add something like hydroxide or any basic reagents to chloroform, because they'll deprotonate it and it'll make carbenes, and the carbenes will run around and attack your molecule. Or it'll explode. I still remember in graduate school one of the graduate students wanting to dry chloroform by adding a little bit of sodium metal to it. That's the way we dry a lot of solvents, because the sodium will react with the trace amounts of water and dry the solvent out, and then you just distill it. I think somebody tried to do that with chloroform. And I think the postdoc walked in and asked him what he was doing. He was like, I'm drying chloroform with sodium metal. And he just looked at him and goes, it's going to explode. And he walked out of the lab. And I think the graduate student was a little freaked out by that, as they should be. So these are relatively easy to make when you want to make them. They're even easier to make when you don't want to make them. So the whole idea here is if you make a carbene, add to double bond, cyclopropane. Stereospecific. So you could go through and write these reactions, the products of this, and we would be in good shape that way. All right, so we will, I guess, talk about the rest of this. We'll finish this topic up, the double bonds, after the test next week. So bring questions. I did, if you didn't get one of the sets of homework problems that are in last Tuesday's folder, they're here. You can pick them up. Any questions you got, bring them to class on Wednesday, and I'll answer them. Otherwise, we'll just stare at each other awkwardly until I don't want to do that anymore.